Hi, I'm Peter Allen from Columbia University. I'm going to talk today about robot path planning as part of the AI course, and I want to talk about some things which are very important. There's a reading reference, Principles of Robot Motion by Theory, Algorithms, and Implementations. It's by a star-studded group of robotics people. You can look at it online, buy it if you need it, but a lot of the material we're going to cover is in this book. So let's get an overview of what we're going to talk about today in robot path planning. We're going to talk about visibility graphs, Voronoi graphs, potential fields, and sampling-based methods. And the sampling-based planners include PRMs and RRTs, and we'll talk more about them as we go along. So let's consider some things about robot path planning. First, it includes spatial reasoning and understanding. Robots can have many dimensions in space. Obstacles can be very complicated, and we need to know what to do when we want to go through these obstacles. First of all, is it global planning? Do we know the environment a priori? Or is it online local planning? Is the environment dynamic? Are there unknown or moving obstacles? Can we compute a path on the fly? These are all questions we have to worry about. And obviously we want to have a collision-free path, but should we path be optimal in time, energy, or safety? So can we compute exact safe paths? It's provably computationally expensive in 3D. The piano movers problem, where you want to move a piano in a complicated 3D environment, is exponential. So therefore we can't really do these things efficiently. We have to find ways to get around these problems. And also there's more than just kinematics. There's dynamics and temporal reasoning that must also be required. So we have to include all of these things in consideration of building a robot path plan. So let's talk a little bit about the configuration space of a robot. This is a mobile robot base with two real differential drive. And the configuration space for a robot is a set of parameters that completely describe the robot's state. So for this little mobile robot, it has 3 degrees of freedom. It can translate in the plane x, y, and rotate theta. It can rotate by changing the direction of the wheels. It can move the wheels together either forward or backwards. So it really has the ability to go in 3 dimensions, x, y, and theta. And so that makes it C-space. It's allowable values of x, y, and theta. Here's another example of C-space. We have a 2-degree of freedom robot, a 2-link robot with a gripper. And you can see it has theta 1 and theta 2, which are the 2 degrees of freedom in the robot's C-space. And what we want to try to find out is, if we look on the left, we see a Cartesian representation of the robot with 2 obstacles. And on the right, we see the configuration space representation of the space the robot can operate in. So we can think of this robot operating either in Cartesian space or in its configuration space, which is these 2 joint angles. So the graph on the right, you can see we have a horizontal axis of theta 1, a vertical axis of theta 2, which shows you the range of legal values of theta 1 and theta 2 that this robot can have. And the dark boxes in the configuration space are the legal ranges. Okay? The white space is what is illegal. Those are configurations which a robot cannot reach. So you can see, for example, the first joint of the robot can only go between pi over 3 or pi and pi over 6, between 30 and 60 degrees. And so we represent that on the horizontal axis of the configuration space graph, so we can go only between 30 and 60. Correspondingly, if you look at the second joint of the robot in the Cartesian space, because of those blockages, it can only go between 0 and 90 degrees, minus 90 and plus 90. So we can show that on the configuration space graph, showing that the robot's ability to move is limited. It can only go between plus 90 and minus 90 degrees. So that's the operational range of the robot in the configuration space. And so basically we have this configuration space, and if we take away the obstacles, then we have what's called C-free, or the free space. So path planning in higher dimensions is important to keep in mind, because even though we're starting to look at little small robots which are in 2D planar environments, we really want to plan in higher dimensions. So for example, here's a planar robot, but it has 8 degrees of freedom. And you can see it blinks and is trying to pick up this green ball, and now we ask it to pick up the red ball, and you can see we have to do planning to get it to that configuration. So the question is, can we plan to make that move between these 2 positions and figure out what all the joints are over time to get it to do that? And we can even expand this to even higher dimensions. Here's a humanoid robot, which has many degrees of freedom. You can see that an anthropomorphic humanoid usually has typically greater than 20 joints. So for example, you might have 2 6-degree of freedom arms, 2 4-degree of freedom legs, a 3-degree of freedom head, a 4-degree of freedom torso, plus up to 20 degrees of freedom per multi-finger hand. So you can see with that many joints and that much mass and volume to worry about, exact geometry and spatial reasoning is very difficult. So this is part of the problem of this higher dimension planning. And obviously complex cluttered environments with lots of stuff in them create more difficulty. So let's take a look at some solutions to these problems and some ways we can do path planning. The first one we're going to look at is a visibility graph. So the question, how does mobile robot get from A to B? Well, let's make some assumptions. Let's assume the robot is a point in 2D planar space. So assume the obstacles are 2D polygons. And we want to create what's called a visibility graph. A visibility graph has nodes which are the start point, where you're starting from, a goal point that you want to reach, and the vertices of the obstacles themselves. And we connect all the nodes which are visible. So a straight line, unobstructed path between any 2 nodes becomes an edge of this graph. And we also include all edges of the polygonal obstacles. And from that, we can create a graph which goes from the start to the goal and use A-star search, which you've learned about before, to go and develop a path which is optimal in some sense. So you can see here, we have a visibility graph. On the left, we have a start and goal and some polygonal obstacles. The robot, again, is a point. And so on the right, you can see that we've connected all the vertices that are visible between the two, between all the obstacles and the start and the goal point, and that creates a graph. And then we can move along this graph to find a path which is the shortest path. So the start goal are vertices of the obstacles, of the graph nodes, and the edges are the visible connections between nodes, including obstacle edges. And again, A-star search can be used to find the shortest path via the visible vertices. And here we can just see what A-star gives us. So now we found the shortest path. So it's a fairly simple idea, and it's provably optimal in 2D that this is the shortest path. Now, we have a problem in that the V-graph algorithm assumes a point robot. But we know a robot has a mass and size. So how do we deal with that problem? The solution is to expand each obstacle by the size of the robot, creating what's called a grown obstacle set. In a sense, we're putting a buffer, a safety buffer, around each object, which is big enough so that the robot can't hit it. So if we stay outside of that zone, then there'll be no contact between the robot and the obstacle. So here you can see a visualization of this. We have a square robot in red, an obstacle which is triangular in blue, and then we can grow that obstacle. And what we can do, you can see how this is done. We have the robot with an origin point, a reference point, and we basically are just moving that robot around the obstacle and tracing out that reference point, and that gives me this grown obstacle. And clearly, if the reference point stays outside the red on the right of that grown obstacle, we will never be in contact with the triangle. So this is what we call a grown obstacle. And effectively, it's shrinking the robot back to a single point. Once we do that, then we can go back and use what we just did before, which is the traditional visibility graph search, to find a path. And that will be a safe path because we're using obstacles which are bigger than they were before, grown by the size of the robot. So the graph search will now find the shortest path, and it may not be a path, it may be blocked using the grown obstacle set. So how do we grow the obstacles? Well, one, you could do it easily enough by doing a reflection algorithm. On the top left, we see a kind of rectangular robot with a reference point at the origin, and we take its reflection. So we take its reflection in X and Y, and we create this kind of inverse object, an inverse robot, and keep track of that reference point. And then what we do is we simply place the inverse object at every vertex on the obstacle. So here we have a triangular obstacle. And once we do that, if you go to the lower left, excuse me, you'll see we can create a convex hull of the vertices created by adding these inverse object to the triangle obstacle. And then if you look at the lower left, you'll see that the convex hull is exactly the grown obstacle which we need, which will allow me to be safe. So again, if we take a look at the robot in the top left, if we take that reference point and move it anywhere outside of that convex hull, we'll be safe. Once we go inside that convex hull, then we'll have a contact. So here you can see on the left we have a point robot path for this obstacle set where we go via the vertices, as we said before. And you can see after you grow the obstacles, the path changes because now you have to worry about getting the size of a robot. So the one on the right is with a rectangular robot in red, and you can see how the path changes because of the size of the robot. Now there's some extensions to VGraph that we still need to talk about. First is rotation. In all the previous examples, the robot was not able to rotate, it just translated. So the question is, how do we add rotation to this system? Well, the solution is to grow the obstacles by a size that includes all rotations. So what you can actually do is you can actually go over a range of rotations, okay, map out the space that the robot takes for that, and then have an encompassing polygon which encompasses all those rotations. So you have one polygon which says anywhere you rotate within here will be safe. The problem is it's over-conservative, so you'll miss some paths because you're making a much bigger robot than you need to get through a very intricate or tight connection area. Another solution is to create multiple V-graphs. So we have a visibility graph for one rotation orientation. Let's do another one for a different orientation. And what we want to do is find regions where these two graphs kind of overlap, where one place where you can rotate between these two orientations. So you can do some of your planning on one V-graph to a certain point where you'll switch to another V-graph at a different rotation, and you'll do the rotation and then continue on your way. And theoretically you can have many of these as layers, if you will, but typically you may only need 2 or 3 to do the rotations that you need. Another problem is non-convex obstacles. So if you have concave polygons or robots, you can actually model them as a set of convex polygons, so you can get around this problem using concave as well as convex robots and polygons. This is just an example of what we were talking about before with the V-graph rotations. So here on the left we have a rectangular robot that can rotate between these two different orientations. And if we try to do an encompassing polygon which takes up all of those rotations, as you can see on the right, it takes up a lot of space, and so it makes this robot look much bigger than it needs to be when we grow the obstacles. So this will miss legal paths if it's too much. So let's summarize what we learned about V-graphs. They're guaranteed to give the shortest path in 2D, which is very nice. The path, unfortunately, is dangerously close to the obstacles. There's no room for error because basically you're traveling right along the vertices and the edges of the obstacles, and there's no safety margin. And further, it doesn't scale well to 3D. So the shortest path in 3D is not via the vertices. So for example, here, as you see in the picture, to go from the start to goal with this rectangular polyhedra, you actually want to go via the edges, not the vertices, for the shortest path. So there are fixes to this, but it becomes a problem. Further, growing these obstacles in 3D is very difficult. So it takes up a lot more time to do this. So this doesn't scale as well as we'd like.